Okay, good evening, everybody. My name is Chris Lambell from the Electrical Engineering Group. Before we get into the main event tonight, just give a quick heads up of the upcoming events. So 9th of June, we've got Sounds Air. Ryan Wardman could talk on Sounds Air journey to date to bring electric aircraft to New Zealand and flights from Wellington, which will be a really cool presentation. 28th of June, we've got Gallagher in again talking on lock technologies and credentials, and that's Kyle Rowe. Then the 14th of July, we've got Schneider in talking on circuit breaker discrimination and cascading. The 11th of August, we've got Enesys, Kane Chapman, who's going to give us an overview of battery technology. Tonight's event, we've got Jonny Parker in to talk on EV charging. So if we could hold all questions till the end, if possible. By the end, we'll pass the microphone around so everybody online can hear the questions, and then we'll read out the questions from everybody online. So I'll hand you off to Jonny. Thanks.
Cool. Thank you. Can everyone hear me okay? That's all on. Okay. Yeah, thank you for having me along, and hello to everybody online as well. I'm Jonny from Thundergrid. We're basically an electric vehicle charging service partner. So what we do is supply and manage EV chargers, and we link them together with the long-term objective to ease the load on the grid as well. So what I'm hoping to run through tonight is trying to make it as informative as I can in terms of any little tips and tricks that we've learned along the way to help plan for EVs, and that's really where a lot of our work sits at the moment. We're doing a lot of feasibility studies to help customers understand what kind of access they need, what type of charging, what type of cost recovery is required in the background. So we're doing a lot of that work at the moment, and that's where we're doing most of our keeping busy. So I'm also a disclaimer, I'm not an electrical engineer, so I'll try and answer his questions as best as I can. But I've been doing energy management for many years with a big focus on energy efficiency. And that's how I got into electric vehicles, because we wanted to basically help the grid decarbonize and help people embrace electricity as a transport and heating fuel. So I'll give you a bit of background on the history of us, and that will hopefully explain a bit how and why we're doing what we're doing. And then I hope some of the information is useful, and we can have some questions at the end, and I'm hoping it starts some good discussion. So just a little rundown of what we're going to go through tonight. So there's a little bit just of who we are, where we came from. Then we've got a bit about why EVs are really important to New Zealand. And then we'll get into a bit of EV charging 101, where we hope to bust through some jargon and what kind of options are out there. Then we've got a little bit we've discovered about how daily range of vehicles impacts design. So that's actually something we found is really important, and it's a big one for us. I'll cover a bit about dynamic power management and how that is becoming a critical player in helping scale EV charging systems. And then I've got a little sort of shopping list of features to look for in charging equipment that's quite useful to make sure it's safe and also to have an eye to the future. We'll cover a bit about cluster design, so how to plan for chargers working together. And a bit about future-proof and interoperability, which is an important one when we're coming into a world of new technology with many different networks and different companies moving into it. We need to quickly find a language that we can all share and talk. Then a bit about billing, data and cost recovery, so some of the back office systems that are available to customers to use. And we'll touch a little bit probably towards the end on what is the future of EV charging, or what's in the near future, and I'll just give some impact on what way we're kind of seeing it at the moment, and then that could be probably a good discussion point for the whole team. So why do EVs matter for New Zealand? Well, basically around 43% of all energy used within New Zealand is for transport fuels. So most of that is imported. We spend about $5.6 billion every year bringing in oil from overseas to then burn in New Zealand. Emissions from transport are rising quite rapidly. It's one area of our emissions pie that is growing. Other areas are shrinking, but transport has been firmly growing. Exposure to diesel particles and things, we know this is bad for health. We know in urban environments that it is not good and causing lots of problems. It's become a major problem in the likes of London and other areas where diesel vehicles really took off. And so it's one that we're trying to backpedal on quite quickly. So what's up for grabs for New Zealand? So if we do manage to change our fuel mix in New Zealand and embrace electricity as a transport fuel, potentially we could have 5.6 or even more $billion back in our economy that's not being sent overseas to pay for oil. So if we can create our fuel locally, we will have more energy security. So we can generate that fuel locally using renewables, which decouples us from any international issues around energy security. And we can also have cleaner urban air. So there's quite a lot of opportunity, even if you're not kind of looking at it from the environmental perspective. In terms of economics and security, electric vehicles actually offer a really, really good prize for New Zealand, which we think could electrify quite rapidly and has a lot more to gain than other countries which have a much higher carbon emission associated with their electricity. So it really is a good option for New Zealand. And electrical engineering, you'll be at the coalface of overseeing this change and bringing about some of that that really good benefit that could happen. So a bit about us. I myself started doing actually residential energy efficiency surveys for the council and for Fletcher Building. I then moved into commercial energy auditing and joined Victoria University as the energy manager there, where I became a lot more aware of the importance of how and when we use power in the buildings and what that means for cost and for carbon emissions. And after doing that contract, I moved on to set up Eco Geek company, which is founded on basically helping facilities and fleets transition away from fossil fuels and planning electromobility and electrification. And electric vehicle charging systems became such a big speciality in terms of what we were doing that we initially pitched the Lightning Lab Accelerator, and we're accepted onto that in the early stage to try and figure out how we could protect the grid and allow EVs to come to the party. So Thundergrid was born, which was it's basically purely focused on easing the load on the grid and really making EV charging smart. So doing more with less is what we were about. So our missions basically is to eliminate emissions through smarter use of power. So not necessarily by chucking in more renewables, by just using power at the right time better can actually have a huge impact and be a lot cheaper to do. To do the heavy lifting in terms of the fleets and facilities moving away from fossil fuel use. So right now we're doing a lot of planning to help places embed EVs into their timelines to actually plan this transition, and that's really where a lot of our consulting work is. So how do we do this? Well, we want to, by easing the load of EVs on the grid. So we've brought in technology from overseas to help that happen, and we're currently an R&D partner for that with them. So we're doing active trials and experiments to improve that the performance of that technology as well. Obviously, electrifying transport is a big how. That's how we get towards that mission. And because of our background is energy efficiency, we also see the opportunities on freeing up capacity to pave the way for more EVs. So having a lens to energy efficiency in a broader sense has proved to be really, really useful. So there's 8 of us in the team. Most of us are based here in Wellington. And we've got folks from different backgrounds. There's Richie, who does, he's from governance settings, so he's from regional council. We've got Joost, who's he's a computer science engineer. We got energy trading networks advisors and some electrical engineers on the team as well. So we're a small team based here, but growing quite steadily at the moment to keep up. So that's the bit about us done. So what I want to do now is just take a dive into the basics. So some of you may already be quite advanced knowledge of how EVs work. So forgive me if some of this is very familiar, but I thought I'd just cover it just to give a good baseline to set for everybody. So what we got here is some diagrams of the different typologies of electric vehicles all the way down to petrol vehicles. So we'll start at this end here. This one here is a internal combustion engine, often known as an ICE vehicle. You've got the engine, which does the traction, and the emissions coming out the back. Then we've got the evolution from that to a non-plug-in hybrid. So this is your early generation Priuses, where it doesn't plug into the grid, but there is a electric motor to recharge some batteries on board from the engine, or when it goes downhill to recover a bit of energy. So we're starting to use slightly less emissions, but basically all that energy is still derived from a fossil fuel. Then we've got what's called a parallel plug-in hybrid, which is where you then have the opportunity to actually charge those batteries from the grid and take advantage of clean energy. So this is getting slightly better. You've still got a fairly complex system where you've got a petrol engine doing the heavy lifting, you've got an electric motor, you've got a battery stack, and you've got onboard chargers to maintain. So we're getting better. That's quite a practical solution for many, but it's still is derived mostly from fossil fuels, as generally the batteries on them are not much bigger than 10 or 12 kilowatts. So quite small range on pure electric. Then we get to a clever end. So this one is a PHEV, which is where you've actually got, it's a battery electric vehicle with a generator on board. So this doesn't power the wheels. This is there just to charge the battery if needed. So this is your BMW i3s, which has a 600cc BMW motorcycle engine in it, just there to top up the batteries if you run out of range and can't make it to a fuel station or a recharging point. So quite a sensible design, especially whilst the cost of battery cells are very expensive, and gets people into EVs, really knocking down those emissions for all their local transport, but gives people some security if they've run out of power. And now we're getting into the world of full battery electric vehicles, where now we're seeing a much greater energy density. We're seeing prices drop. So we're seeing full BEVs coming to market that are now reachable. And this is currently the goal for most government agencies. By 2025, they want to see up to 16,000 vehicles from government full battery electric. So there's a lot of work to do in planning for that infrastructure that's going to be required to recharge these vehicles. But the prize to the agencies and to the clients is huge. Very big fuel savings, lower maintenance because there's no clutches, there's no air filters, there's no oil filters. Maintenance is a lot simpler. So they're pretty good. So what happens in an EV? How does it work? So basically you've got what's called your traction battery. Now this is the main big battery that does the driving, drives the electric motor, which drives the wheels. You've got one critical thing here, which is called the onboard charger. Now this is often a cause of a lot of confusion. So when we put out a charger, AC charger, it can basically give a car up to 22 kilowatts if it's a 3-phase charger. But not all cars can drink 22 kilowatts. On AC power, they can only drink whatever their onboard charger is built to supply. So if you've got a first generation Nissan Leaf, for example, it could plug into a 22 kilowatt AC charger, but it would only be able to drink 3.6 kilowatts. That's its maximum charging speed on AC. So basically this is a rectifier. It brings the power into the car, converts it to DC. It then sends that via the battery management system to charge the traction battery. And that's how most EVs are charged, using plug-in chargers over AC. Now, many will also have a DC rapid charging port. So that's a separate socket on the car that will send a DC power that's already converted to DC straight into the battery pack, which means it can charge a lot faster. So generally EVs have 2 ports, but it's the onboard charger that we pay a lot of attention to. So That's a little sort of overview of what's inside electric vehicle and what components are quite key for it to be charging. Now, in terms of the WorkSafe or international standards, these charging is divided up into modes. There's different modes of charging. So mode 1, you won't hear very much. Mode 1 is basically golf cart charging. That's, you know, it's not really in the EV spectrum. Mode 2 is what's called an in-cord protected device. This is where you've got one of these, which is basically you've got a little brick that's called your EVSE, and that plugs into your 3-pin power point, and that's designed to deliver up to 16 amps. So a small amount of current, but is generally not favored because it carries a lot of risks at scale. You've got then mode 3, which is typically a wall-mounted or a hardwired AC charging station that's designed to communicate with the car and has additional safety features. It's hardwired with a dedicated circuit back to the point of supply. Then we tip into the DC side of charging, which is mode 4 DC charging, often called fast charging or rapid charging, or even ultra charging. So this is where you've got really fast charging going directly to the battery. This is not something you'll get at homes. It's not something you'll get typically in buildings or facilities. This is roadside. I need to charge quickly and be on my way charging. Now, in terms of the modes, this is the modes 2, which is basically what you can either have a 3-pin plug. Sometimes people use a Blue Commando or Caravan sockets to help deal with the temperature that can build up on the socket over time. It's generally under WorkSafe, and most the coming standard, it's basically not advised. It's really, they're really trying to push it out because there's a lot of safety issues around that, which I'll cover off later. Mode 3, so this is where you have charging stations, which should ideally be socket based. You can get ones which are tethered, but you've got to be really sure that you only need to service one type of EV from that. And they typically have 2 sockets, 2 typologies, one called a Type 2 and one called a Type 1. Type 1 is common in North America and Japan, and therefore we have a lot of Type 1 in New Zealand because we've got a flow of second-hand EVs from Japan. Type 2 is a European standard based on what's called Menekes, which is becoming the global standard. It can actually carry a lot of current and deal with a lot of things, that particular socket. And then we're into mode 4, the DC side, where typically there's mainly only 2 protocols. One is called CHAdeMO, and one is called CCS, which stands for Combined Charging System. So you might notice that this and this are very similar. It's because it's actually the same. It's one socket for AC and DC charging. So if you're on the AC side, you plug into this top part of it. And if you're doing DC charging, you've got a plug that covers the whole thing. And these are your 2 DC pins at the bottom. So it's quite a clever socket. And Tesla, who have been running their own protocol for many years, are now moving over to this standard. They're starting to play in with the global standard. So we're starting to see some really good solid standards emerge. So in terms of scale of mode 4 DC rapid charging, we start down the bottom end, which is typically where you'll get 25 kilowatt DC chargers. Quite practical when you've got a dwell time of a vehicle, maybe 40 minutes to an hour. Pretty good at refilling most common EVs and quite practical. Then you've got 50 kilowatt, which is a good balance to have as a decent roadside charger or a forecourt charger. These ones are Trillium built units. They're built in Australia. Then we go up a level to the likes of Deltas and ABBs as well, which will have 150 kilowatt charging capability. Most EVs, the first generation, could only charge at around 50 kilowatts on DC. That was their top charging speed. We're now getting EVs that are capable of charging 100 kilowatt or even more, mostly in the luxury line of vehicles at the moment. We then get into high performance ultra charging. This has been very much driven by Porsche, who created the Taycan, the EV capable of charging 350 kilowatts on DC. It's quite a lot of infrastructure that you would need to reinforce these chargers, which are capable at 350 kilowatts, a liquid-cooled cable. So quite a lot of current, and those vehicles can recharge in 5 minutes at that, which is phenomenal technology leap. But obviously it comes at a huge technical challenge in terms of the infrastructure and the price for it. So we're watching that one closely, and we'll have that discussion, or it comes to at the end to see what we think the future of mass charging will be. Now, the EV charging is a lot of jargon around it. It's quite confusing for customers. It's very difficult for people who haven't got an EV to try and understand what these terms are. So it's just one to quickly highlight some of the key terminology, which is obviously EVSE, which just stands for Electric Vehicle Supply Equipment. There's the BMS, which is the battery management system. When it's on a vehicle, that's the thing that's basically orchestrating which cells get charged and how much. There might be 90 or 130 cells in a vehicle. So the battery management system is doing the balancing across all of it as the current's coming in from the onboard charger or straight from the EV charger. There's state of health, which is a common term used for the health of the battery and how much it can degrade by. State of charge, this is how much the battery is full. What's the full percentage of the battery? Now, one thing to note about state of charge, it is only reported to DC chargers. The vehicle reports its state of charge to DC rapid chargers. The vehicles do not report their state of charge to AC chargers. It's a different protocol, and the vehicle manufacturers have...
Sorry, Johnny, I was just going to say there's been a comment to say, when you're pointing at the slide, people can't necessarily see what you're pointing at.
Yeah, okay.
Yeah, the frame of the camera sits perfectly between the screens. As soon as you point at something, so if you can describe verbally what you're pointing at.
So
Thanks.
I'm pointing to the one that says state of charge, and that is basically where it's out of 100%, how full is the battery. And what we found is quite interesting is that data is sent from the vehicle to the DC charger, so the DC charger can know how much power to give the vehicle, because that's coming in at higher current, but it is not reported to AC chargers. AC chargers just blindly give the power until the car says I'm full. So that's a difference there to be aware of. Then there's in-cord protected device, which is one of these mode 2. We call them granny chargers because they go really, really slow. Perfectly fine if you've got a small battery EV like a Gen 1 Leaf, but when you start getting into the like...
I say pick it up, Johnny.
Do you want to pick it up? Yeah, sorry. When you start getting into the realm of larger battery EVs, not so practical because it could take days to recharge your car using that. So that's where we start seeing a need for higher powered AC chargers. Then there's what's called J1772. You might see that. That is just a type 1 connector. It's just another name for type 1. Then there's the 62196, which is the protocol name for a type 2 connector. And then you've got CCS, which I just covered earlier, which is the combined charging system, which is that socket that looks like a flower with two ports below it. And then you've got the CHAdeMO, which I always think looks a bit like a pig. I don't know if you see the same, but I see it like that. And then there's one which is a common term to look out for, and if you're looking at hardware for EV charging, is OCPP. It stands for Open Charge Point Protocol. So it's quite critical. That is basically a software language that EV chargers should talk in order to be linked to any cloud e-mobility platform. If a charger doesn't talk OCPP, it can't be networked with e-mobility platforms. So it's important to have something that has a global standard for its software. Otherwise, the chargers can't be smart controlled. They can't be interlinked with billing systems. There's a lot of things that can't happen. And there's a group called the Open Charge Alliance who get together and write those protocols for all the manufacturers to follow, including the OEMs. So we're really fortunate that they nipped it in the butt before EVs took off and got round the table to at least discuss a global language that chargers should use to talk to EVs, and then for the chargers to then talk to the cloud platforms that run all those services. So if you've ever got customers coming to you saying, you know, we need an EV charger, we need a few, there's some useful sort of questions to kind of unpick slowly with them, and they won't always know the answer to it. But one of the things is where do you need these chargers? Is it going to be in a private area, or is it going to be, is it a public use? Are you going to need a billing system? Is this going to be for a marketing purpose, or is this going to be roadside in any way? The other one is dwell time. So how long is the vehicle, the EV, going to be parked for? So some people might come to you and they might be from a BP station. Hey, like, we need an EV charger. You know, and slow AC charger is not going to be doing the job for them, because people are going to want to fuel up, eat a pie, get gone. You know, that's what they need. They're going to need a high-speed DC charger. Likewise, if it's someone with a vehicle fleet, it might be, okay, how long is the fleet berthed overnight? And it might be 6 hours or so, or it could be a courier company where time is money, or a taxi, and they need a reasonably steady turnaround of those vehicles. You might be, you've only got 3 hours to recharge them. So the dwell time is really critical, understanding exactly what they need. The other one is access. So how do they need to lock those chargers down? Is it in a secure environment where it's only available to a select few people, in which case you might not need access restrictions? But if it's in an open car park, an area where other people could plug in, so it's asking those questions to see what functionality you might need from the charger. This is the one that we get as well. So this is daily range. We're finding is really critical if you're dealing with mass EV charging. So if you've got a client who's from a corporate and they've got 30 vehicles that they're looking to transition to EV, you could take the approach in designing for worst anger. So you've got 30 chargers and here's the maximum current they could all draw. Therefore, the pipe has to be this big. But actually, what happens then is that it's a massive cost, a big upgrade, and it's more like just turn the client off and they won't do anything. So what we found, actually, the reality is quite different when we look at vehicle data. So if they use eRoad or vehicle tracking, to get that daily kilometers that each vehicle's traveling can be very, very informative to help you design the charging logic that goes with that, to actually understand what the true power requirements on the site are likely to be, but also having room for that to grow, and also having safety measures to ensure that if you've ever underballed it, they're not going to have trips. So daily range we find is critical information, and if we get government agencies or corporates coming to us, we try and get that, and then we compute it back to see what the kind of power demand will be. And the other one is, if they know it, what brand and models of EV are they looking to bring in? Different brands can charge at different speeds and will ask for different amounts of current. So if we know that, we can map that power demand against what that onboard charger. So we find very much daily kilometers divided by EV efficiency equals your power demand, so your overall power requirement on site. So one thing you can do is look up the vehicle efficiency in terms of how many kilometers it typically does per kilowatt. It's kind of miles to the gallon, you know, it's the same thing. We often design on a very pessimistic 5 kilometers to the kilowatt, and that means that you've coming at it still from a fairly conservative view. But we find that's useful just to work it back and find out, well, what is actually the power demand? Do we actually need a 22 kilowatt charger, or have they got 6 hours to recover, you know, X amount over that period of time? So you take your daily range and then you divide it by the EV efficiency, and that basically gives you the recovery kilowatts needed. So when you know how many kilowatts a vehicle might need to recover its range, so say it's doing something like 100 kilometers, then that might need somewhere around maybe 20 kilowatts to recharge that. So you've got 20 kilowatts that needs to be delivered overnight, and then you can map that against the dwell time or charging window to actually see how these can start staging together. So once you know your recovery kilowatts that are needed, you can then divide that again by the charging speed of the onboard charger on the car. And that then gives you the hours that's capable of recharging that range. So you then know you can start playing with things to start seeing, as we scale, we might have 30 or 40 EVs on this site. The reality of what they need is quite different to designing on the label and the charger, so long as you've got those safety measures around if they all do happen to ask for 200 kilometers to be recharged all at the same time, you've got that covered as well. But the reality is most vehicles are only doing around 60 kilometers a day. So it's in a fleet context, it has everything to do with that data. And sometimes we find, yep, vehicles are doing a good range and we need to assign enough capacity to them. And other times we find there's lots that just doing short trips. So lots of opportunity to recharge. So we've often done we've built various different calculators over the time that we've been doing this to try and help figure out things. So one thing is, once we know what kind of spare capacity is likely to be on the fuse board, we look at the energy data from the site to see how that capacity is actually punching. So we might look at the time of use data. It could be from clip-on metering to see how many amps per phase are actually being used. So then once you've got a good feeling for how much spare capacity is available, you can start putting in, on here we built it so we can put in the kilometers that each vehicle is likely to need every night, mapped against its charging speed, which then tells us how many hours it's going to take to recharge those cars if we're using dynamic power management to manage the charging speed. So if all the cars, all those chargers are talking and sharing a bandwidth of power, you can actually charge a lot of vehicles, because you'll find the very load within the building changes throughout the day and there is spare capacity to drink up. So we found basically dynamic power management changes everything. You can charge a lot of vehicles with relatively challenged connections. So I'll go into that now, which is a little bit, here's a rough sort of diagram on how it works. So that grey line is, say, your typical building load. So as you can see, it sort of comes up and it might peak towards the middle of the day. You know, you've got the office is full of people, the computers are humming, you've got the HVAC going, lift going up and down. Then say you add uncontrolled EV chargers, or the EV chargers have been allowed to evolve without any kind of strategy behind them. It creeps up. So if people come back, they plug in the morning, so they've taken the fleet cars away, or they've plugged in that morning, then all the HVAC's fired up, and that load has started to increase towards that dotted line, which is the fuse limit. So if you didn't have any dynamic power control happening, you're likely to trip that fuse and that building could go dark. Or if it's the like sort of a house, you know, that could be the pole fuse, which is very awkward. So what we're trying to do is police that line and make sure we can have our cake and eat it by absorbing that, being able to access that spare capacity that sits above that peak or around it, but without ever pushing it beyond that line. So that's what the load guard does. I've got one with me here. It's quite simple. It's basically essentially a backnet device that you've got CTs, current transformers, that clamp around your incoming main. And then that comes to this little box which goes on the DIN rail, and there's a little Ethernet socket. So we run that then to an Ethernet switch, which then on communicates with all the chargers. So this little box here communicates with a lead charger, and it tells it every 0.25 milliseconds how much current is available at any given second. So those chargers can react and adjust according to live building loads. So if the lift suddenly fires up and your current is getting drunk up, or there's a big set of hot water cylinders that click in, any kind of loads, they're detected, and the chargers will adjust themselves around those loads. So domestically, these are really useful as well, because as people get inductive cookertops, they've got ovens, they get home, it might be a winter night, light to night, or a southerly, and they fired on the electric heating, plugged the car in at the same time, and normally that would trigger a fuse trip. But if they've got one of these, it means the car is slowed down, allowing them to heat the house, And when that load drops back, the car will be brought back up again. So it's automatic and it's local, which is really key. There are similar things that can do that, but it's reliant very much on a continuous cloud connection to do that computing. And we warn against that. It's better to have something that you can set locally, that it just works irrespective of being connected to the internet. So these are really, really critical. And we're finding that with dynamic load management, it opens the door to do a lot more with a lot less. So that's one thing we install pretty much in every job we do, and it really makes a big difference. So with some of the chargers that we install is that you can have what's called a cluster. Now, a cluster is a group of chargers that talk to each other to share load. Clustering should always be, again, locally offline, not dependent on a cloud connection or a subscription. There should be hardware talking to hardware within your building. You know, you shouldn't have pay for an extra service to get that to work. So the computing power in the chargers is that there's basically it's a computer. One of the chargers becomes a lead, which then is instructing the others on how to behave. And they're constantly comparing notes with each other on how much each one of their EVs is asking for. And they can then adjust their charging speed based around a machine logic, which can also factor when that person needs to leave. So if you've got someone who needs to go, they've just got into the office, they've got to be out again for a meeting. If they put an exit time on the charger, on the touchscreen, it means they will be removed from that pool of energy management, and all the other chargers will be pulled down a little bit harder to compensate for them. So the system makes an assumption on how long it's got to recharge, and it balances that load across them. So a single charger can handle the computing power for up to 30 chargers. If we tip over that, we install a central computer on the fuse board that takes over the logic, which can go up to 200. So the load guard feeds into that and provides that live power information for that to work. We also put in safety measures. So whenever we're trying to design the charging logic with the customer, we try and think about, well, what's the worst scenario? So if someone comes along and cuts that link, that hardwired link between the load guard and the system, what's the fallback? You know, if you've suddenly got 20 cars all trying to charge, you want to make sure if that load guard's suddenly removed from the mix, that they're all going to operate to a safe level. And there's a raft of programming functions we can put in there to make sure, together, they either don't exceed the fuse limit of their assigned distribution board, or we can have them all drop to a safe level of charging, which might be 8 or 16 amps, that we know that connection can handle without dynamic load management. So the idea is to stop the trip and then re-establish those comms quickly. So again, making that local is really key because it's faster and reacts faster. So we can also balance them across the phases, and on the software of each charger, what we typically do is tell the charger if you've got a single phase EV plugged in. Most EVs on the market are single phase. So balancing chargers across the phases and telling the software which phase it should use to charge a single phase car is quite critical because it evens things up. But at the same time, you know, if a Tesla pulls in that can charge 3-phase, you've still got that functionality if it's 3-phase cabling to those chargers. So in terms of a design, we sometimes just do sketches like this to try and sort of explain a bit about where they might be sited, and we work a bit with the customers to figure out what their parking needs are and where they go. So often, yeah, you might recognize this one. So here's an example where you've got a main switchboard, and then you've got a dedicated EV DB. By having a dedicated distribution board for EVs, you can support growth. And it means you can have one central point they can all come back to. And then we can either make sure all the chargers don't exceed the ability of that EV DB, but you can also have the chargers flex up and down according to what's happening even further upstream on the main switchboard. So if your main switchboard's getting quite close, it could also power manage those EV chargers, even though they are still within the realm of their own distribution point. So dedicated DVs is really good. And basically how we typically do it, we have it could be a single phase cable or a 3-phase cable coming from each EV charger back to that EV DB, but also a Cat6 Ethernet cable then we have a DIN rail mounted Ethernet switch, which means it can all come back to one point, and you've got this core service where all the chargers can grow from. We can mechanically limit clusters. So we could say, hey, you 10 chargers all together as a team, never use more than 200 amps. And they will all check with each other to make sure they don't equal more than that. So you can do it without a load guard if you've got smart chargers with solid state switches that can increase or decrease their current as allowed. And then you can have the load guard feed into that. So a common board design, one thing we found quite useful, if there is power supply to support it, is to consider an MCB channel per parking space. Even if you've only got, say, 10 out of 50 that are needed, then it's going to be quite clear. It's not going to be long before there's phone calls for more and more and more, because different tenants need EV chargers. So if you're putting in your central core services, having enough ways to support those additional parking spaces is quite good. If there's a DC power supply, we try and put all the comms in the same place, so that can power the Ethernet switch and often a gateway modem. So we found it's more cost effective and easier to have a 4G modem, which acts as a gateway communication for all the clusters, because otherwise you'd need potentially a SIM card in every charger, which gets quite costly. So if you're looking to have all your chargers networked and reporting back to a cloud platform, often using a 4G modem, we configure these and do them as standard, is a really good way to go, because it's outside of the customer's internet network. It means if they're worried about security, those kind of issues, the EV charging infrastructure is completely independent of it. And often it means we can then get in and change and commission and do configurations remotely, which is really, really useful. So RCDs, they can either be installed on the fuse board. A lot of our hardware, you can order it with an RCD inside, which saves a lot of real estate on the switchboard. So it's already inside the unit as an option. So sometimes the boards, we might recommend an antenna as well to go off it, just to boost any 4G signal. And the load guards you can either put them in the main switchboard, or you could put them in the mechanical board that you might be feeding from, anything upstream. You can also put them in your EV DB if needed, because then what that will do is if you do get a third-party charger that's not connected to that cluster, i.e. can't talk to it, it means the other chargers will pick it up and they'll adjust around that fixed load. So it's a good one if you do have third-party chargers that want to come back to the same place. So we also, in terms of good choices for future-proofing, we align with the NZTA guidelines, which basically says to really choose socket-based mode 3 chargers if you can. We've got for a long time, we're going to have a mixture of EVs that will have type 1 connectors or type 2. But by having a socket-based standard, it means you can service all EVs. Tethered is convenient for users, but it really means that parking space is only suitable for one type of EV. So it's not practical in the long term. So we recommend socket-based. If people want to leave cables there, they can. A cable can be locked into place, but it means it can at least be removed if you've got a different type of EV, making it quite easy for users and future-proofs it. So yeah, a type 2 socket is often known as a Menekes, and is the most common global standard. So we strongly recommend going socket-based. As you know, there's the WorkSafe guides, and there's the coming New Zealand standard as well, which is just coming out of draft form. to try and provide some basic guidance around installing. It all basically leans quite heavily towards mode 3 charging being the option, and with its own dedicated feed from any point of distribution. And a Type B RCD or a Type A can be used if the station has DC leakage detection in it. So if it has that, it functions the same. Okay, I had to whiz through this. So the isolator switches should cut the neutral, and basically anyone should check that the MEN link is in place. If you're doing chargers that are external, it's good to make sure that you've got local electrodes or a mesh for local earthing as well as bonding back. And all stations should monitor the earth continuity and should shut down if that is broken. If it detects that it's interrupted, then the station should not provide the current to the EV. This is one thing that we've found, that not all smart chargers are equal. There are different types of smart charger out there. I'll start at the end there, which is what's called the in-cord protected device. These are slow chargers. They can be convenient for affordability. You can get them for about $600. Currently used by first-gen EV owners domestically, but can pose a lot of problems in terms of people using extension leads, dragging them through puddles, not being connected to a socket that's rated for the continuous current they deliver. If you follow a lot of the EV groups online, you'll commonly see some melted plugs, and there's a bit of a risk. So I can see why, as EVs scale, it's important to try and move that to one side, because they are actually determined as emergency chargers. If you read the EV instructions, they're not meant for daily use. Then we start going up to the next level, which is a hardwired Type 2 socket. So that one is better because it is hardwired and it avoids that issue of uncontrolled extension leads and plugs. But that's what we class as a dumb charger. It doesn't talk to the building, it doesn't talk to a cloud platform. So it's just a static plug and go charger with no smarts. Next level up, we start slightly smarter. We've got a charger that is capable of talking to a cloud network. So it's capable of monitoring the power consumption for billing or for data management. It's capable of having RFIDs to activate charging, but it doesn't talk to the building and it doesn't cluster. So it's a slightly smarter charger. And then you've got the E-Trail units, which we like, but there's other ones. Schneider now are coming to the market with something a bit smarter. And I believe there's some ABB as well that can also do this. It's where it's starting to take either a feed from the electricity meter or start to use external sensors to adjust its charging speed and start to share power. So we're getting smarter units, and we're trying to really get people to choose the smartest, because it will cover all bases as EVs grow in New Zealand. So truly smart chargers should really have communication via 4G, Wi-Fi or Ethernet. They should all be OCPP 1.6 or above, and that OCPP should be unlocked. Some will say it's OCPP, and it is, but it's locked to one cloud network. It's kind of like a mobile phone. You get it, you want it unlocked to work with different networks. So watch out for that and really ask, does that mean it's only going to work with one cloud platform, even though it's got OCPP? Clustering should ideally happen offline and locally. Dynamic load management is, in our view, is a big must if you can get it. We think it does change everything, unless you've got a supply where you're confident no other charging is needed, ample electricity to go around, then it might not be needed. Earth monitoring is a must. We do advise getting units that are built for 3-phase. So right now, most EVs are single phase, but we're watching quite closely, because as competition heats up between the vehicle manufacturers, we don't think it will be long before 3-phase rectifiers become more affordable, and the likes of delivery vans will start wanting to charge at 3-phase. So having the hardware in place that you can later upgrade and add those additional cables to means you've just avoided a whole world of e-waste. So having something that's 3-phase that can operate as single or 3-phase is really good. DC leakage protection, that means you can use a Type A RCD. upstream or within the charger, and that saves somewhere between $200 and $300 per installation. So worth doing. Internal RCDs are do save that cost as well in terms of switchboard space and cost. And we really like the solid state switching. So if you've got inside the charger, it's not a dumb switch going off on. It's something that can modulate from 6 amps up to 32 amps up and down in a smooth fashion. So solid state switching really improves that curve and helps it. Onboard computers are really good because they mean as well the charger can be reconfigured and reprogrammed for a different purpose. So if it needs to be redeployed to another staff member's house, or the setup changes, or the capacity of transformers upgraded, you can jump in and it can be reprogrammed to work with all that. And RFID is useful because of fleet activation and assigning it to users. So that's the, I might skip, again, so making it sure it's socket based. Sometimes if you've got anything that's Modbus integrated, that really helps as well. So I'll just like to run out of time, so I'll flick through some of these. These are some of our, in terms of our systems where we can get in and configure chargers locally on the onboard computer within each charger. And that's where we can start putting those current limits around the building and around the cluster and get them all working together. Users can also statically set if their energy price changes at different times of the day. They can have a script which is within the charger, and it will speed the charger up or slow it down according to how their network tariffs work. That doesn't need to be connected to our Thundergrid platform to work. That's all local. Now, looking at the software side, this is where it's the cloud service that is connected to that charger. Again, what's really critical is having open source hardware that could be linked to any platform. So our platform, like we're really big on load area schedules. That's what we're testing right now with Transpower and others, because as EVs scale, we need to make sure the grid is the low voltage grid is protected, and that what we want to do is link in those chargers, connect them with an ICP, and eventually it means the networks don't have to start charging people more money for electricity because they've got to upgrade all their transformers. It can actually be controlled, and I'll get into that later. There's a thing called OCPI as well. This is a back office terminology that means a cloud platform can communicate with another cloud platform. So a network like us could integrate with ChargeNet, for example, and users can share equipment. Much like you can go to an ATM and use an ASB if you're a KiwiBank customer. We need to get to that space and quickly in New Zealand. Otherwise, we'll end up with a very muddied, because lots of other networks will come in. So we need to really encourage OCPI, which we use, we're ready for it. And we want to start partnering with, playing with others to try and test that and get it working. EV Roam, you'll see that in the New Zealand standard. It is a database which you can connect your cloud platform to report location and availability of EV chargers. It's a database that was built before the global standard was set, so it doesn't use OCPI. So it's one to consider. I'm hoping they rebuild it to the global standard so we can all interface with it. So customers can also have portals. This is what we set up with people. We set them up with their own portals for their own portfolio of chargers. So they can log in anytime, see the real-time power usage, see the status of the sockets. They can export their electricity data. They can see how people are using their infrastructure. And we also produce environmental reports for them, so they can start getting a really good insight into how their fleet's being used, which can then be useful for planning more EVs or expanding their public charging network. So we want to enable people by not being the network, but providing the tools so people can run their own show, and we just support them to do that. So again, so software future-proofing, making sure the back office software is open source, that data is available for the users. The back office uses OCPI, it's ready to interface with other things, and ideally has APIs. Now we're trying to get to a space where we're equipment agnostic. So one thing I think is really good is if you do deal with any cloud software provider, is to ask how many chargers they're integrated with, because the more brands that cloud partner is integrated with, the more they can help with, basically. So we're currently 37 brands of charger, So we can work with lots of different ones. There's cost recovery that can happen through that as well. So we can automate the cost recovery between landlord and tenant, body corp and tenants, or commercial landlord and corporate that's renting the third floor but needs 10 EVs on the basement. So all that is solvable and can be automated. So no one's having to go and read little meters or do it into billing. So it's all possible so long as those chargers talk OCPP and can be networked to a cloud platform. Now, outside of what we're trying to do there, we want to solve some bigger issues, and there's ones that affect New Zealand but will affect other countries as much. And one is the low voltage grid, which is the risk that EVs pose to that. So in terms of peak demand, if you've got a suburb where half the street suddenly add an EV, that's about a 50% additional load to every house. So it's going to cause the low voltage grid issues, and they're going to either have to invest in upgrading power infrastructure, and that can affect the most vulnerable in society because the cost of power will go up for everybody. So what we want to do is try and make sure the lines companies can have the levers to not do that, to actually not have to upgrade all that infrastructure so quickly and not increase the price. So local overload is also a risk, which is what the load guard is there to solve. So there's two problems that we're solving now. We're clustering chargers geographically and assigning them under the low voltage network provider. So eventually we can build up aggregated load that can help either Transpower or help low voltage networks manage that flow of energy as EVs scale, because it's going to happen really fast and we're trying to get ahead of it. So this is actually why we're called Thundergrid. We want responsive load that is connected and is serving everybody. The other one is the electricity cost. So the cost changes for users at different points of the day. So rather than manually changing the configuration of each charger, you could actually just issue a schedule online to 100 chargers in your network to slow down when your power price is high. So, and then we're looking at making that automatic in terms of that, can we tie in APIs? Now, one of the big reasons why we got into this was around the emissions profile of electricity, because it's one thing to go to EVs, but it's not so great if you're burning coal to charge it, right? So we need to get ahead of that. And this is really why we've built Thundergrid, because we want to solve this issue here. And then we want to take it into Australia as that starts decarbonising to make better use of renewable energy and put it into the EVs and lower that emissions. So the problem we have is thermal load is fairly static. It's baseline. So often people are charging EVs at night. It's mostly thermal load that's running at night. So the emissions profile of the EV is actually probably higher than people think because of how and when it's charged. But if we could link what generation is online, what is producing electrons, interlink it with the load and interrupt that load to ideally have thermal, gas or coal shut down, that's where we want to get to. So by doing these load area schedules, networking everything, we can slowly start designing out fossil fuel peakers, and then we can start re-looking at how people could push a button to say, only charge my EV at this point during the day using dynamic load management, so I can be sure it's being charged by hydro or by solar. So there's different tools that we're working on building and transitioning to, so we can make sure EVs are even cleaner. So it's that local control, it's consuming energy at a time and in a way that supports the grid, but makes better use of renewables and designs out those fossil fuels. So that is what we're trying to build in the background. Now this leads me on to the end bit, which is about what's the future of EV charging, and it's really hard. I call it the Wild West at the moment, because every day there's a new announcement of battery or a new type of charging system or things, but we're pretty sure we've landed on a standard in terms of the Type 2. And the big question for us is really about AC versus DC. What is going to be the most practical way to recharge EVs? And it depends on which camp you're in and in terms of what your actual operation is. So here's a company called GridServe in the UK. They're building roadside, these are like motorway service centres purely for EVs. So these all have 150 kilowatt rapid chargers lined up with a cafe, and it's meant to be a place to stop and recharge for 20 minutes. And this is what they're building up and down. So they're going heavily into DC charging, thinking the fuel station scenario is still very relevant, but being topped up with, you know, a coffee experience and a, so that's one way the industry's going. But that has challenges, you know, so we're talking, often we talk to, like, you know, rural fuel groups are like, well, what do we do? Like, we don't know, EV's a thing, you know, and their supply is a very small transformer rurally. It's not possible to put a 300 kilowatt charger. So we're trying to figure out how we can, you know, how these can come to the party and provide EV charging services when it's very skinny. So these are some of the challenges in the future to solve. This is what's happened in Australia. There's a group called JetCharge, which is ChargeFox, and they recently deployed a couple of 350 kilowatt DC chargers, again in an area that needed reinforcement. So that big switchboard was installed, a very large transformer, a 500 kilowatt battery buffer was installed with a 250 kilowatt grounds solar array to provide that energy to recharge those batteries, coupled with the grid as a hybrid system, so that could support that high rapid DC charging. Whether that's overcooked, I don't know, because that's probably a, you know, $1 million at least. It's going to be a very expensive way to refuel your car. So, but this is just an example of high power DC on what sort of challenges are going to be needed to do that. But we're taking a different view, and we're not sure if we're right or wrong, but looking at the International Energy Association research, most EVs are charged overnight by plugging into AC. It's convenient. People don't need to go to a fuel station anymore. They can recharge at each end of their destination, at the hotel, at work, or at home. They no longer need that fuel station experience of refueling. So if we're coming at EV charging with the old mentality of we need a fuel station experience, I'm not sure it's going to work. And there's one thing that might tip it, is energy density. As EV batteries get bigger and more dense, people are going to have more and more range. So they won't need to stop necessarily at roadside rapid chargers, because they will have enough in the tank to go from here to Topol quite easily without stopping. They can charge at their destination. So coupled with convenience, we think AC charging has probably the most practical deployment. The chargers cost about $3,000 versus $50,000 for a DC charger, and you can serve a whole chunk of EVs rather than just one at a time. So as power density increases, we think that will change how the industry. Now, DC will always be needed for commercial vehicles, fast turnaround vehicles. It is not going to go away, it's needed. But we're just thinking about the mass consumerism, like what are the masses going to do in terms of those fleet, those drivers. The other one is habit, because some people might leave it to last minute to charge. They might run it right down to zero because they just keep forgetting to plug in, and they might be the customers for a DC rapid charger. But if most have the habit, like our phones, we just plug it in when we get home. It's a different mentality. So habit will very much drive the future. So AC fleet charging with smart control in terms of interruptible load, we think is very much what is needed and what's practical and efficient to deploy. We're watching very closely on the right. There is a vehicle to grid charger, which is bidirectional. So the EV could support or put power into the home or into the facility at about 8 kilowatts. So we're watching that space. We're watching developments in America, which are doing that with school buses. We're not sure the feasibility yet of vehicle to grid, because the cost of equipment and the complexity around doing it is at a practical deployment point. However, if you've got a big battery on likes of a bus, vehicle to grid is something that's worth looking into. But for light passenger vehicles, we're not sure that technology stacks up, because interruptible load is probably a better way to manage that. So yeah, that brings me to the end. That's us. We're an electromobility service provider, and yeah, open up to some questions.